Welcome. In this video, I'll be constructing confidence intervals for a population mean using the student t distribution. A confidence interval constructed from sample data is a range of values that is likely to include the population parameter at some specified confidence level. The confidence interval for a population mean is determined by taking the sample mean, the point estimate, and subtracting and adding the margin of error to it. As seen in an earlier video, if we assume the population standard deviation is known, the margin of error is determined by this formula with a z critical value. Since the population standard deviation is usually unknown in practice, it is substituted with the sample standard deviation, which requires we use the t distribution. The t distribution is similar to the standard normal distribution in that it is also bell-shaped, has a mean of 0, and has an area of 1 or 100% under the curve. It, however, has a standard deviation greater than 1, which makes it flatter than the z distribution. While there is only one z distribution, there is a family of t distributions with the shape of each determined by what we call degrees of freedom, df for short, which is based on the sample size n. For the confidence interval for a population mean that we're concerned with here, the degrees of freedom is n-1. Here is the t distribution curve for 2 degrees of freedom, for 5, and for 30. We see that as degrees of freedom increases, the t distribution approaches the z distribution. Here is a sample of the t distribution table. We have the degrees of freedom on the left here. At the top, we have the right tail area of the distribution. In some tables, you will also find 2 tails alpha, and some will also include confidence levels. The t critical values are shown in the body part of this table. The values of z are usually shown on most t tables. They reveal that as sample size or degrees of freedom increases, the t distribution approaches the z distribution. In constructing the confidence interval for a population mean, given the sample standard deviation, the margin of error is given by this formula, where t alpha over 2 is the critical value. That is the value we look up in the table or obtain using software with degrees of freedom n-1. S is the sample standard deviation and n is the sample size. Alpha is the significance level, which is 1 minus the confidence level. So for a 90% confidence level, alpha will be 0.1, and that is divided equally into the 2 tails. The values corresponding to these boundaries of the confidence interval are the critical values. Suppose we have a sample size n equals 12, then the degrees of freedom n-1 will be 11. On the t table, at 11 degrees of freedom, we can look up 0.05 in one tail or 0.10 in 2 tails, or 90% confidence if we have it. The corresponding critical value will be 1.796, which will be negative for the left tail here and positive on the right. Let's look at some examples. A random sample of 15 observations has a mean of 20 and a standard deviation of 3.5. To estimate the population mean with 95% confidence, that is, at the 95% confidence level, we want to first determine the margin of error and then the confidence interval. The sample size 15 here is considered small because it is less than 30. Sample sizes that are at least 30 are generally considered large enough for the central limit theorem to apply. Therefore, we have to assume that the population is normally distributed in order to safely proceed with our calculations. If the sample size is large, that is at least 30, this assumption is not necessary due to the central limit theorem. Now, for n equals 15, degrees of freedom n-1 is 14. So for 95% confidence, or alpha 2 tails 0.05, the critical value is 2.145 at 14 degrees of freedom. The margin of error is therefore about 1.94. The lower limit of the confidence interval will be the sample mean minus the margin of error, and the upper limit will be the sample mean plus the margin of error. To interpret this, we say we are 95% confident that the true population mean falls between 18.06 and 21.94. In essence, we're saying that using this method, we expect to capture the population mean 95% of the time. This interval constructed, however, may or may not contain the true population mean. Let's look at another example. Here, the sample size is increased to 85, and we want to construct a 99% confidence interval for the population mean. The sample size 85 here is considered large because it is larger than 30. Therefore, according to the central limit theorem, the distribution of sample means will be approximately normal for a sample size this large, and the assumption of normal population is unnecessary. In general, since sample size is in the denominator of the margin of error formula, increasing the sample size alone will decrease the margin of error and consequently make the confidence interval narrower. On the other hand, reducing the sample size will increase the margin of error and make the interval wider. In contrast, a higher confidence level will produce a larger critical value, resulting in a larger margin of error and thus a wider confidence interval. With n equals 85 in this example, we have degrees of freedom n-1 equals 84. Now, note that most tables will not have degrees of freedom 84 on them, so you can use software if applicable. Otherwise, you can use the closest degrees of freedom available in the table. At 99% confidence level with df equals 84, the closest df here is 80 with a critical value of 2.639, which we will use here. The margin of error is therefore about 1.00, and the 99% confidence interval will be from 19 to 21. That is, we can be 99% confident that the true population mean lies within this interval. Again, this means that if all possible samples of 85 are taken from the same population, we expect 99% of the confidence intervals constructed from them to capture the true population mean within their interval. This interval constructed here is just one of those many intervals. And that's confidence interval for the population mean using the t-distribution. Thanks for watching.